Hello everyone, this is lecture 23, Cylindrical and Spherical Coordinates. At this point, you may see a pattern that is developing with respect to integrations. In Calculus 1, we introduce integrals of single variable functions. And then in multivariable calculus, specifically in the last 3 lectures, we move up 1 dimensions to double integrals of 2 variable functions. And in this section, we take another step and investigate triple integrals of 3 variable functions. So it's not as straightforward as a single variable calculus when you look at double integrals, or in this case, triple integral. The problem gets a lot more difficult, a lot more involved when you consider the regions of integrations. When you evaluate double integral, you see sometimes we need to convert the region from a rectangular coordinate system to polar coordinate system. And when you get to triple integrals, you may run into a similar issues. That is, for some regions of considerations, such as spheres or cones or cylinders, having a regions written in terms of rectangular coordinate system or Cartesian coordinate system may feel awkward and complicated to just even look at it, let alone evaluate the triple integral. So what you can do is that you can convert the descriptions in a Cartesian coordinate or rectangular coordinate to another coordinate system. And that is the idea of this lecture. That is, we want to be able to write down the formula that connect the Cartesian coordinate to other coordinate system, that is cylindrical coordinate system and spherical coordinate system. So hopefully at the end of this lecture, you could be able to derive the relationship between cylindrical coordinate and rectangular coordinates and vice versa. And also you could be able to derive the relationship between spherical coordinate and rectangular coordinates and vice versa. So what is the cylindrical coordinate? It's actually very simple. This is just the extension from polar coordinate system that you already seen in the last lecture or previously. In cylindrical coordinate system, a point in space is represented by the order triple of r, theta, and z, where r and theta are the polar coordinate of the point's projections in the xy plane. So r and theta is the point on the xy plane, and you again have seen that already in polar coordinate system. And z is just the usual z coordinate in the Cartesian coordinate system. So basically, the point on the cylindrical coordinate system is just the extension from what you already seen in Cartesian coordinate and polar coordinate. Again, so the conversion between cylindrical coordinate and rectangular coordinate is that it's just a simple extension of 2D polar coordinates to the 3D space. The combinations of polar coordinates with the z coordinate system as presented here in the order triple of r, theta, and z. So the descriptions for r is how far you want to go out from the origins. So how far you want to go out from the origins, and this is where you have r. Theta is how much you want to rotate, or the angle between the positive x-axis and the line segment between the origins and the point on the xy plane. So this is the point on the xy plane, and this is the point of the form r, theta. And theta here is how much you want to rotate from the positive x-axis to the line segment connecting the point and the origins. And z is from this particular point how high in the positive direction you want to go up, or how low in the negative direction you want to go down. And that's how you obtain the point in the cylindrical coordinate system. It's very simple, it's very straightforward. Again, this is just a simple extension from the polar coordinate system that you see in the past. Because of that, many formulas from the polar coordinate system can be transferred to cylindrical coordinate system. That is the relationship between x and y with r and theta. So x is equal to r times cosine of theta, y is equal to r times sine of theta, x squared plus y squared equal to r squared, or r is equal to square root of x squared plus y squared. Remember, again, when you take the square root on both sides of these equations, you're going to get plus or minus. But in this particular context, r is a distance. Therefore, you just choose a positive square root of x squared plus y squared. And z is equal to z. Alright, so this is one set of equations you can use to convert from the point on the cylindrical coordinate system to Cartesian coordinate system. So let me note that. So cylindrical to rectangular or Cartesians. Now, what about when you have rectangular coordinate system or Cartesian coordinate system, and you want to convert that into cylindrical coordinate system? So you have another set of equations that you can use. That is, cosine of theta is equal to x over r, sine of theta is equal to y over r, And tangent of theta is equal to y over x. And again, z is just equal to z. So using these two set of equations, you can go back and forth between cylindrical coordinate and rectangular coordinate with ease. So now let's take a look at the following example. You want to express the point of the form 4 pi over 3 and negative 2 in cylindrical coordinate to rectangular coordinate. So that is the point given to us has the form r theta z. So to convert this into rectangular coordinate, you use x equal to r times cosine of theta, y is equal to r times sine of theta, and z is equal to z. For r is equal to 4 and theta is equal to pi over 3. So you get 4 times cosine of pi over 3, or 4 times 1/2, this is equal to 2. And for y you have, this is 4 times sine of pi over 3, or 4 times square root of 3 over 2, or just 2 times square root of 3. And z is just equal to 0, which is equal to negative 2. So the point in rectangular coordinate is of the form 2, 2 square root of 3, negative 2. Now in example 2, you want to convert the point 1, negative 3, 5 to cylindrical coordinate. So the point given to us is in rectangular coordinate. So the point has the form x, y, and z. And you want to convert this point into the point of the form r, theta, and z. So to get r, you're going to calculate square root of x squared plus y squared. For x is equal to 1, so 1 squared, and y equal to negative 3. And you're going to get square root of 10. For theta, I'm going to use the equation of tangent of theta equal to y over x. So tangent of theta equal to y over x, or theta is equal to r tangent of y over x, or this is equal to r tangent of negative 3 over 1, or this is equal to r tangent of negative 3. Because x is equal to a positive number and y equal to a negative number, therefore the point 1, negative 3 is in the fourth quadrant on the xy plane. So theta has to be the fourth quadrant on the xy plane. And again, z is just equal to z, or equal to 5 for that matter. So the point in the cylindrical coordinates is of the form r equal to square root of 10, theta is equal to r tangent of negative 3, and z is equal to 5. Again, for theta is in the fourth quadrant on the xy plane. Now let's move on to the next example. In this example, you want to convert the point negative 8, 8, and negative 7 to cylindrical coordinates. That is, the point is given to us in the Cartesian or the rectangular coordinate system in of the form x, y, and z, and you want to convert that point into the point of the form r, theta, and z. So for r is equal to square root of x squared plus y squared. Well, this is equal to square root of negative 8 squared plus 8 squared. And this is going to be equal to 8 times square root of 2. For theta, I'm going to use the formula tangent of theta equal to y over x, or this is equal to 8 over negative 8, or this is equal to negative 1. Therefore, theta is equal to r tangent of negative 1. Because tangent of theta is equal to negative 1, the reference angle that we need to look for is pi over 4. In addition, the x value is negative number, the y value is positive number, so the point xy is in the second quadrant on the xy plane. And therefore, theta in this case is going to be equal to 3 pi over 4. And z is equal to negative 7, so the point in the cylindrical coordinate is the point of the form a times square root of 2, 3 pi over 4, negative 7. So that's it for the example related to converting between rectangular coordinate system to cylindrical coordinate system and vice versa.